All right. Thank you so much, everyone, for joining. Good morning. And thank you so much for participating today in our webinar, the Learning Tree International Decision Analysis Moving Beyond Data webinar, presented to you by Learning Tree author and instructor Andrew Tait. My name is Darby Jago, and I'm one of the product managers here at Learning Tree. And before we start, I do want to take a quick moment to introduce you to the Learning Tree Anywhere platform, which is what we're using today. If you've ever participated in a Learning Tree class as a live virtual attendee, you'll recognize this layout, as this is what we use in our Learning Tree courses. So you'll see that our presenter, Andrew, is in the upper left-hand corner of your screen. Below Andrew is our chat box. Looks like a lot of you are using it this morning to say good morning. So good morning. Not sure if you all have snow where you are, but I know the States is pretty much covered right now. So, and then next to that in the top middle, or actually in the middle in general, you'll see our presentation. And we had those poll questions below that we've gone ahead and closed out for now. So please, enjoy the webinar. Andrew, if you want to go ahead and take a moment, introduce yourself, and we can get started.
Sure. So first of all, we're looking for questions in the chat room. If I misquote Voltaire, we should judge people by their questions rather than their answers. I prefer that definition. You've probably been in these kind of things before, where people say there are no stupid questions. I'm not going to say that on the internet. Clearly, there are a lot of stupid questions, but if you ask good questions, we'll definitely judge you by those. So that's going to be good. So my background is very data centric. I'm gonna rip a little bit on data here in this discussion. But before I do, I want to say that I love data. Right? I've spent a career in data. My background is actually artificial intelligence. My first degree is in artificial intelligence. I've been in it for a long time, and throughout my project, I've built a lot of database systems, data-driven systems, data-informed systems. So there's no one who loves data more than me. Yeah? I kind of live data, but I've got slight concerns these days, and that's that we're kind of fetishizing data. And we have this kind of thing where we believe that we can just take data, shove it in a big tub, stir the tub, and out comes some amazing insights. And I think that's dangerous. We have this kind of like mantra: if only we had more computing power, if only we had more data, wisdom would actually rise to the top. It's just a case of not having enough data. And we're increasingly seeing this as a software problem. We've got these libraries and we get software developers in and we say, hey, just kind of like use these libraries. It's all been done for you. Stick the data through it and out will come the answers. So we're really getting into this thing. We have this cult around data, that data can solve everything for us and data is the only thing we need. And more data will be more smart, will be smarter, and more computing power, more data. That's what will drive us forward. But I think we're losing quite a lot when we do that. And I'm going to talk a little bit about some of the problems with data, then talk about some of the tools we might use if we actually want to really understand the types of decisions we're making. And that's really what we're trying to do, isn't it, with data? We're trying to actually focus on decisions. Every year you get these kind of, the start of the year, and we're obviously early in the year at the moment, you get these things, don't you? What are the top 5 things that will happen in your industry this year, right? You get those blog posts, you get all those kind of LinkedIn things. And every year for the past 5 years that I've looked at these things, one of them is always democratizing data, i.e. managers will be able to go onto a platform and actually analyze their own data and get some results from it. And every year it doesn't happen. It's a bit like a self-driving car, right? Every year we expect it to happen, it doesn't happen. But every time I see people advocating this democratization of data, I kind of die a little inside, because it's actually so hard to get the right conclusions from data. And if we actually don't step back and think about decisions we're trying to make, we're going to get all sorts of trouble. And again, this is part of this fetishization of data, this cult of data that we seem to be involved with now. I want to talk about some of the problems. Don't get me wrong, there's a lot of statistical techniques out there that we use that can solve these kind of problems and can help mitigate these problems. But the reality is we don't use them. In day-to-day decision science, day-to-day data analysis, which is what I'm really interested in talking about here. In companies, I constantly see this business of just taking data from a database that you have, or data from a data lake, we've got all these data lakes now, and we stick it through the models, and out pops the answer, and kind of we run with that answer. No one is actually using any of these more sophisticated tools. Well, the bulk of people that I see making use of these techniques in companies are not really making use of some of the more sophisticated tools. So, unless we actually kind of start to understand and the relevance of these tools, some of the challenges of data, we're going to continue to make these same mistakes. And you see a lot of organizations start off working with data and they fail to get value from it. They start off these programs and they want to know, well, what kind of problems can we tackle with it? Or why are we not getting the benefit out of investment in this? And it's because of this obsession, I think, with data and the focus on data, as opposed to focus on data as one tool in kind of trying to make more scientific decisions, if you like. So if you just think about the basics of data, we talk about kind of like, when we talk about numbers. And if you think about, this is the kind of election, obviously, in 2016, American election. And you've no idea how hard it was to actually get images of these two people that weren't unflattering, yeah? I mean, these two people obviously incredibly polarizing, and every image I could find was actually rude about one or the other of them. So it was a bit of work to get icons that were kind of this nice. But this was the predictions about who would win the 2016 election, and these were on 538. What does this actually mean? We throw these kind of numbers around all the time. But what do these numbers actually mean? What does it mean that there's a 29% chance of Donald Trump winning the election? I mean, you sit down and think about it, it's actually quite a difficult thing to actually work out what you're trying to say. And yet we throw these things out all the time when we're doing data analytics. But I would suggest that we very rarely step back and think about what the meaning of them is. And if we don't have a meaning for it, if we can't interpret them, it's a bit dangerous to actually be throwing these kind of numbers around. And you could say that, the classical statistical interpretation would be, well, if we kind of ran this election 1 million times, 29% of them, Donald Trump would win the election. And if Donald Trump was 29% to win the election, yet he won it, that was considered a huge problem as well. People were going, well, the polls were all wrong. Well, the polls weren't actually wrong. 29% is not 0%, right? There are problems with the polls, but you have to be careful in how you interpret these numbers. So even simple numbers like this, there's a massive amount of interpretation and we have to do behind it. And what these really mean, these numbers, is that in a model we built, a small world that has nothing to do with the real world, basically. We're trying to represent the real world through a small world model. In the small world model, when we ran it thousands of times, in 29% of those simulations of fake small world, Donald Trump won, and in 71% of those, Hillary Clinton won. But unless you understand what that model is, that small world model, you've no way of actually interpreting what these numbers mean. Yeah? And again, we rarely actually give people the model, do we? When we give them these numbers, we don't go, oh, and here's the model. Here's a detailed description of this Bayesian model that we built. But unless you interpret these numbers, no, we just throw those numbers out. And without that kind of wider context, without an understanding of how these kind of models are generated, it's almost impossible to interpret the meaning of these simple values that we see spread around all the time. So it's a huge problem what these things mean in the first place. And I fear that one of the problems that we create when we focus on this data is we start to infantilize ourselves. There's been research that shows that sat-navs actually physically affect your brain and the part of your brain that would be involved in reading maps. I mean, when I was young, we always had to buy a map when we learned to drive and went to a new area. We moved house, we actually bought a map of the area, and we got an idea of our geography, where we were in space. But actually, the use of sat-navs, you don't think of that anymore. I mean, I moved into my current house about 6 years ago, and actually I know less about the geography of this area than anywhere I've ever lived before. And the use of these technologies tends to involve in a loss of environmental engagement. And I fear that kind of this automated decision-making process where we get the data and out pops the answer, that's what we're trying to get to, actually involves us in that loss of environmental engagement in our businesses and our organizations and in the process of actually making decisions. And the more we disengage from that and hand it to the data, the less control we have. And as I'm arguing, data is actually quite limited in what it can do anyway. So we're actually in danger of losing quite a lot as we fetishize data and data analysis. Data analysis clearly has its role, but we need to actually make sure its role was appropriate. And what we tend to do when we've got this, when we get data, we get so much data now that we tend to get into this trawling business if we're not careful. If you don't start to think about, the statistical consequences of your data and how your data actually kind of needs to be interpreted, there's a danger we trawl for insights. And if you've got a ton of data, it's easy to trawl that data for needles in your statistical haystack, your data haystack. And we can find all sorts of interesting things that are just arbitrary in the data because we've got so much data that randomly we can find all sorts of things that just aren't true when you actually test them. But the data, if we look hard enough, actually will kind of suggest to us that this effect is actually in there when it's not. As Robert Course said, if you torture the data long enough, it will confess. And we're doing a lot of data torturing as we trawl these huge data sets looking for insights without actually thinking about whether those insights are just spurious. And you've probably all seen some sort of spurious correlations. There's a lot of them around. There's actually a site that deals with just this. And if you trawl the data, you can find all sorts of things. And there's a guy called Tyler Vigeland with a site called Spurious Correlations. And he actually kind of finds all these things. So for example, we have per capita consumption of margarine in the US is highly correlated with the divorce rate in Maine. I don't know if there's anyone from Maine and whether you tried actually kind of not eating as much margarine to see if it actually prevents you having as many divorces in your state. But I wouldn't bother because clearly it's just a completely spurious correlation. But if you trawl the data for long enough, if you use data tools hard enough, you will find things like this. And this is massively compelling, isn't it? Look at that. It's like a 0.99 kind of correlation between consumption of margarine in the US and divorce rate in men. Clearly, there's no causal relationship there. It's purely a spurious correlation by looking at enough data. If you look at the data long enough, you look at enough data, you'll find things that just aren't true. And you can find all sorts of things like this in your own data sets as well, because we've just got this massive data now, and we can mine it for this kind of stuff with the technology we have. But it doesn't mean that it's something useful. Statistically significant, all those great things, doesn't mean it's actually useful. If we focus on the data, we end up with these kind of paradoxes, basically, these pathologies. And it's really the difference between prediction versus understanding a lot of the time. If you just want to predict something, then you don't really have to worry about having a theory about how A causes B or A causes Z. Yeah? You can just look for these kind of correlations, say, well, these things are related. So if we see a change in one thing, we're likely to see a change in the other thing. That's fine, but usually what we want to do is we want to affect the change, don't we? We don't just want to know that something is going to happen and we stand back in business and actually just watch it happen. It's not what we're trying to do. What we're trying to do is intervene. And if we want to intervene, we have to understand the causal relationships. You know? And statistics is all about finding associations. Actually, where it doesn't help us really at all, and there are techniques that can, but it's classical statistics actually doesn't deal with causation at all. That's it, everything is association. From the turn of from the start of the 1900s, decided that statistics wasn't really about causation. Causation wasn't important. It was association was important. But as living beings working with things, we're always looking at causation. We're always looking for causes, right? We interpret these graphs, these correlation graphs. We interpret them using the language of causation, even though that's not true. We're desperate to actually add causation into the mix, because that's how we work with the world. It's how we understand the world, and it's how we manipulate the world. And without Data's not really going to get us there. We need different tools to get us there. We need tools that involve us in understanding the systems that we're working with, understanding decisions, the consequences, the levers that we have in those decisions. And it's very easy to abuse data, isn't it? We all understand about lying with data. I mean, how many times have you come across that kind of like idea? But even in real world situations, really important situations, people can actually massively misunderstand data and numbers that are drawn from data and statistics, basically. Statistics, as we'll see, can help us, but just actually blindly following data and blindly following statistics that come from data can have huge consequences. What this slide is suggesting is a thing called the prosecutor's fallacy. You may have come across it before. And the idea is that the probability of observing some evidence given that someone is innocent is very, very different than the probability of someone being innocent given the evidence was observed. So, for example, let's take the lottery, the national lottery in the UK. I think there's a 1 in 43 million chance of winning the jackpot, something like that, right? So, what's the probability of me having a lottery win given I'm an honest person? Oh, 1 in 43 million, right? I mean, I'm an honest person, you'll have to believe me, okay? But if I go out and buy a lottery ticket, there's a 1 in 43 million chance that I'm going to win that, yeah? But flip it around. So, given I've won the lottery, what's the chance I'm honest? Is it 1 in 43 million? Well, clearly not. I presume that most people that win the national lottery are honest people. They're not fiddling the system. It's quite a hard system to fiddle. So I presume that the probability of you being an honest person if you won the national lottery is in the 90%, if not higher. Yeah, so it's highly likely that you're honest. So flipping that around is quite important. And you may think, well, so what? But actually, there was a thing in the UK where a woman was convicted of, she was charged with murdering 2 of her infant children. And a prominent pediatrician gave evidence that ended up convicting her. And he argued that it made a huge number of statistical mistakes, actually. Very eminent pediatrician made, and his statistical evidence, which is what basically convicted her. She was convicted on statistical evidence, really, and there were flaws in all of it. And the Royal Statistical Society, wrote about this and complained about it. And she was eventually released, but ended up killing herself. It's a tragic story. But this expert said that there was a 1 in 73 million chance that her 2 children could have died. Two children could have died independently, and so that was taken as a 1 in 73 million chance that she'd be innocent. Well, clearly that wasn't the case, because the chances of actually 2 children, of someone murdering 2 of the children, are phenomenally rare. They're much rarer than 2 2 children dying of natural causes. So the Royal Statistical Society did some analysis and decided that there was a 5 to 1 chance that she was actually innocent if you just take statistics into account. So actually from a 1 in 73 million chance that she was innocent to an 80% chance or above that she was innocent is quite a shift. And with something this important, shows you how badly these things can go wrong. And this kind of and here is an example of an extremely important situation, but in day-to-day business, this sort of confusion is happening all the time with a misunderstanding of statistics and how they operate, because statistics is incredibly hard to think about. It's a very, very hard thing to reason about. There's an eminent a statistician, ex-president of the Royal Statistical Society, Cambridge University, emeritus professor, and he says that whenever he's confronted with a question about probability, a high school question about probability, he has to sit down for an hour with a pen and paper and work it out before he can give you an answer, because it's just not intuitive. So we've all got to be careful when we're dealing with all this data and massing it up and drawing kind of numbers from it automatically, as we might do in the democratization of data. and assuming that we know what's happening, because we can be massively led astray. If humans struggle with this, how's a computer going to do it for us? And data isn't even immune to our biases. I mean, we take data, we assume it's going to be something that's completely, we assume data is completely objective, right? But it's not. And how we interpret that data, how we reason about that data, how we perceive it, actually has a huge impact on what we do with that data. So for example, we have all sorts of biases that we can introduce, even if our data is good. We've got a thing called the replication crisis in science for the past decade. People have been worrying about it. And part of that is selection bias, where the only papers that get published are the ones that are actually successful. So it's only positive results that get published. But if 1 in 20 results are significant, you might find that for every paper that gets published with significant results, there were 30 that failed, but we never see those 30 that failed. So we believe that theories are true, even though it was just random kind of like luck that one study attributes significant results, and that's the one that gets published. It's the only one we see. So we believe that everything is actually, that we believe that the theory they came up with, even though if you looked at the wider evidence, it would show that it wasn't true. So again, the biases that we bring to it, we add to the data, and our use of the data are quite significant in determining the value we can get from data as well. So what do we do about this? It's a problem, right? We got this data, we're obsessed with this data, we're kind of, we're building these tools that just take data in a pipeline and produce an answer, and we want to take the human out of the loop more and more and more. And we think that's a good plan, right? Because if we're using data, then, data is truth, right? Well, clearly it's not. There's all sorts of problems that arise with data. But what do we do with it? What do we do about that? Well, I think there's a couple of things we can do about it. I think, first of all, we talk about data science, and I think we have to actually start doing data science, right? We have to stop just getting all the data and shoving it in the pot and mixing it and hoping we cook the right answer. And the way that we do data science, I would suggest, is we have to use statistics, and we have to have more statistics in our data, in the way we're using data. And I think we've actually drifted away from statistics. A lot of data science or data analysis we now do, people are just avoiding all the statistical work. And I think, if you're going to do data science work, you have to get yourself that strong grounding in statistics. Without it, interpreting the data correctly is hugely challenging. Now, it doesn't have to be that, the same person that's doing the data wrangling has to be a statistician. Maybe it's just part of a team. But unless you've got heavy statistical oversight, data is going to lead you astray, especially with all the amount of data we have. We've got so much data that we're doing this data dredging, and we're finding things. And without the statistical tools to test whether these things are significant and valid, we're going to struggle. Without tools to think about the problem in the first place. So that's the first thing I think we have to do. And the next thing I think we have to do is we have to start modeling our decisions, not our data, right? We have to start with the decision that we want to make. And that provides the context. And without context, data is going to be all over the shop. And that context is hugely important to us in actually understanding what we can do. So I think we have to start thinking first. We have to recapture what makes us fundamentally human and start thinking about things and not just handing it over to the data. Don't hand control to the data. When we've thought about the problem, then we bring data to the party. We may not need data. Data is great if you have it and it's relevant. But if it's not relevant and it's bad and it's badly collected and it's biased, it's the worst thing you can have, because people will actually point to it and say, but the data says something different. But if the data is garbage, who cares? And a lot of data is garbage out there. And the only way we're going to find that is to think about the problem first. So we really need to rediscover some of the old techniques. We did not rediscover decision analysis. We've got tools to help us do this, to think about problems scientifically, mathematically. And I think we've just pushed that to one side, and we've kind of obsessed with data. And I'll talk about decision trees to show you how obsessed we seem to become. I'll talk about decision trees in a following slide, but actually if you search for decision trees, all you'll find out about is machine learning. Actually finding out about analytic decision trees, which have been around for decades, it's actually quite difficult because of the obsession we have with these automated decision analysis tools. And we need to accept that we'll blind spots. The thing with data is because we always think that data can answer every question for us now, and we'll have blind spots, and we just have to accept that we'll have these, and sometimes they're massive. Sometimes we can't answer the question with data or with the current state of thinking we have. So, we've just got to accept that sometimes we've got to go with that leap of faith when we're making decisions. And we need to contextualize the data, and that's what we're doing when we're thinking about decisions first, putting the data in context. So we want to go through a cycle of this data and building a model, statistical model or kind of mathematical model, whatever you want to do. We've got some kind of model. And then we're using expertise to look at that model. So we're bringing our expertise and we're challenging that model and thinking about how likely that model is to be true. And that model is informing that expertise as well. So we have this joint play between the expertise and the modeling. And then that leads to a decision. Then the decision leads to an action with an outcome. And we can make mistakes in all those parts of the process. The action might not result in the outcome we thought we'd have, in which case we're back analyzing the data and going through it again. But sometimes we don't have data and models. Sometimes we just have expertise. Sometimes, it's impossible to model given the knowledge we have and we don't have any data. And that's fine. We can still make decisions. We still do make decisions, right? So we make decisions without data. Why do we have to, obsess about kind of like sometimes we have to, do nothing but data? So I think, we have something we can do about it. And, there are a whole bunch of processes you can follow, decision-making cycles. This one's fairly popular. There's one called bulletproof problem solving, which comes from McKinsey, which is quite interesting as well. But, think about the problem first. Focus on what you're trying to do. Then create a plan. And only then think about the data. Only then care about the data. If you've got some data that can actually help you with this problem based on your plan, that's great. We want to use it. We love data. But, we need to make sure that we've got the data we need and it's going to help us solve the problem. Then we do some analysis, which may involve the data, may involve just analyzing our understanding of the problem, because we'll see there are tools for that. And then obviously conclusion, and what we might conclude is that we didn't understand the problem correctly, so we're back to actually looking at the problem again. Yeah. So the first thing I said was about better use of statistics. So what I'm talking about here is bringing science to the data. Data science, not just data, right? We talk about data science. Well, let's actually try and understand what the science is in this data science. And I would suggest that really what data science is just computational statistics. I'll wait for the arguments, right? But to me, that's what it is. We're using computers to actually study, to help us work with statistics. I don't quite know what it is if it's not that. I think that data science is a reaction to statistics, not caring about how the data was got in the first place. But I don't think that's true anymore. I don't think there's a statistician coming out of a degree now in their early 20s who isn't heavily involved in using computers and kind of understanding the issues with data, et cetera, et cetera. So I think if there was a distinction between statistics and kind of data science, it's actually becoming less and less. Statistics has realized that this is a big deal, and just focusing on kind of like treating data as plumbing is no longer actually viable for their field. So there's a number of things we want to do. So first of all, we want to actually have hypotheses when we go into these things, and you very rarely see people do this. But unless we have a hypothesis about what we're trying to get from the data, we'll dredge the data. If we don't know what we want the data to tell us, and in tons of business cases, this is what I find. They shove the data in and hope insights come out. Well, yeah, insights will come out and they will be wrong in a lot of cases. You need to go into that data with an understanding of what you expect the data to tell you. A hypothesis, which is just statistics has always done. And if you then change the hypothesis but actually use the same data, then you're data hacking, you're data dredging, you're p-hacking. So you need to actually have a hypothesis before you even approach your data. You're not doing that. You're not even doing basic statistics. You're not even doing that. Statistics is the science of learning from data, right? So where's your science if you're not even doing that? And we need to, if we're trying to get causality, and I've said, unless we can't get causality, we can't actually intervene in changing the situation, right? If we can understand what's going on, the association's great, but if we can't intervene, what is the point? So if you're looking to intervene, then the gold standard, I guess, we're actually trying to understand causality from data is a randomized control trial, where we have kind of a treatment group and a control group. So, if you've got give a bunch of people COVID vaccine, give a bunch of people placebos, and see if it makes a difference. And then we're controlling for all the other factors in the data. So again, we need to conduct experiments, and experiments are a huge part of data science, really. A lot of companies are doing this A/B testing. And that's a huge value, a great thing actually to doing with data. Experimenting, setting up experiments where you collect data and then analyze it. It's quite a powerful way of actually making use of data. So companies that are using it for experimentation tends to be quite a good way to go. But very few companies that I experienced are doing that. And there are other statistical tools like Bayesian statistics. So there were, that's about really looking at what these numbers mean is a start point. If we go back to my 71% for Hillary, 71% for Donald, then we have kind of what do we mean by those? When Bayesian statistics, we say that's a degree of belief, right? About how much we believe that Donald Trump his chances of winning are, and how much we believe that kind of Hillary's chances of winning are. And we can actually, Bayesian statistics gives us a really nice model for learning from data, for updating our beliefs based on new data coming in. And that can kind of make sense of some of these numbers in some cases. So there's lots of things we can do to bring more science to how we look at this data. And I think, a lot of that is just making use of the statistical tools we already have. Let's bring statistics back from the brink and start to say, look, it's not just about hacking some Python code together. Let's actually use the tools we have to be a bit more rigorous about the science we're bringing to our data. And once we've done that, that's kind of like looking at, reining in the data a little bit, but looking at starting modeling decisions rather than the data, I think is probably where the bigger value for me is. Statistics is still about just taming the data. We're still very much data focused, but actually I want to start focusing on decisions so we can work with decision makers. That's the first thing. If we give everything to data, we kind of like hand over to the computer, we hand over to the statisticians, if you're sensible enough to have statisticians, but we really lose the involvement of decision makers because statistics is so complicated. Traditional statistics is a big complicated thing, right? I've been doing it for 20 years. It's still complicated. It's not intuitive, and so we can't expect people who don't have a quantitative background really to fully understand the consequence statistics, and that really pushes them out of engaging in the decision-making process. So I think we need tools that directly involve people in the decision-making process. So for example, here I mentioned decision trees, and if you search the web, just try it if you want, and you'll find all about machine learning, right? The type of decision trees I'm talking about are very different. They are kind of like decision analytic decision trees. And here what we're doing in the decision tree is we're mapping out the stages, the sequence of decisions. So I have to make this decision before I make that decision, and then I have to, when I've made that decision, this event might happen with a degree of probability. So I'm actually understanding the structure of my decision. I'm taking a complex situation and breaking it into the stages I have to understand. So you'll get an example of someone deciding, do I use Excel or buy a specialist tool? Then if they buy a specialist tool, like a deep learning tool, for example, does that technique become widespread? If so, my investment in the specialist software as a consultant would pay dividends. If it remains niche and no one's interested in it, I'm going to lose the money I invested. So I can start to actually look at the chains of kind of like possible outcomes I can have, score them all up, look at the likelihood of them, and then work out what the best decision is for me. The key here is that I'm explaining, I'm clarifying what the process is. It's not just that I guess the answer, I'm breaking it up into small bits that I can think about. And here I can use data because look, I've got numbers here. What is the probability of a technique becoming widespread or not? Well, there's forecasting. I can use data to try and understand that, historical data possibly. How much am I going to make? How much business is going to be coming my way? Well, that can be kind of like, demand forecasting. So I can certainly use data in this model, but I'm not starting with data. I'm starting with understanding the structure of my decision. And then it shows me where data could be valuable. And the point about that is I don't just end up using the data I have available. If we focus on the data, we just take what we've got and shove it in. But we may not have the data we need. If I start with the decision, I can see if I have the data I need to address that particular part of the problem. If I don't have it, then I'm just going to have to estimate it. Yeah. So, because it's an important part of the decision. And I may not have often don't have the data that I need to make a decision. Well, using these kind of tools lets me see that. So if I've got, a decision to make that involves multiple stages or, different stakeholders, I can use that. If I'm looking at choosing between different options, then again, I can start to break that down. So let's say I want to look at education and I want to look at, what sort of school is best for children. Then I can take education and break it down. And here I've got two different models. Well, we could start by breaking education down to STEM and liberal arts, which is how a lot of education is kind of broken down. And the moment we think about that, right? Oh, you're going to be a liberal arts major or a science major or a STEM major, right? It's this, I don't know if this is an American term, Americans use it, but it's science, technology, engineering, and mathematics, right? So, that's how I often think about education. But is that a good way to think about it? Or should we be thinking about education as giving us a broad range of skills? Because, so many kids come out of a university with a particular niche specialization and go straight into something else. Because there might be no jobs in that area. I mean, if you've got a degree in history, very few jobs that actually need that degree in history. So you end up getting a job that's nothing to do with history. Well, shouldn't we actually be giving them general purpose skills? Like, shouldn't we be focusing on statistical reasoning, communication skills, complex problem solving? And that's not, this forum isn't the place to solve that, but I'm just showing that you can have two different models. And if you model the question in different ways, you come up with different answers and get different insights. And again, data is not going to tell us this kind of thing. This is a creative process we have here. And I can show you an example of using this kind of modeling to choose a car in Excel. There's a spreadsheet behind here. We can get into that if we want to, if we've got time. If you've got interest in a particular model, I'll go into in some more detail. But here, what we're doing is once we get to the bottom here, well, these lines would be scoring them. So for example, let's take the bottom one. And if I think the statistical reasoning is the most important, I'd give that 100. And then I would say complex problem solving, maybe a 70. And then communication skills, maybe a 50. Then I put weights on those. I put weights similarly on the ones below. So if we're taking statistical reasoning, I say, well, what's most important statistical reasoning? We don't to understand uncertainty. Well, let's take, that 100, risk can be 80, simulation can be 60. And so I score those things up. And then for all the possible universities that I'm trying to rank based on the quality of education, then what I can do is score them based on uncertainty, risk, simulation, emotional intelligence, so on and so on. And then by weighting up my criteria, I'm able to see what I would value based on my decision criteria the most, right? So again, I've broken the problem down so we can see what really matters to us. And then I'm able to use simple mathematics to just point me in what might be the right option for me or right option for society if I'm doing a policy study. Yeah. So again, simple mathematics, but again, when I'm getting those numbers, I can start to draw in data. So I could do opinion polls to see what the weights of these things should be. Do people value statistical reasoning in companies more than communication skills? Let's do a poll and collect that polling data, and there's my numbers. Let's score universities on, let's get data on how much research universities do in each one of these areas. So when I score them, I'm using data. Yeah. So again, focusing decision first that I want to make in the structure of the decision and bringing data in context so I can see whether the data I have is relevant or not, and where I have data, I use it. But when I don't have data, I don't try and throw away my decision and just work with the data I have, because that's not going to get me anywhere. So I need to have tools that actually make clear decision to me. Here we have a technique called confrontation analysis based on game theory. And here is what we look at when we've got multiple stakeholders, each with conflicting objectives. So what you do is you actually define your position. So here we've got the coalition. This is a kind of simplified situation of some work I did when I was in defense. We've got coalition, and the coalition wants the warlord to fight terrorists and provide intel. And if the warlord does so, the coalition's offering to provide force protection training, give them some control over the aid, and will crack down the criminal activities. They're not going to accept criminal activities, which is what the warlord might want those to be left alone. And similarly, the warlord, and then what they're going to do if they don't get what they want. And this results in a number of what we call dilemmas. And resolving dilemmas actually is what you have to do to try and get people to accept your position. But again, this is about focusing on the decision. It's about the structure of the decision. And with this particular model, what you find is that to actually get that first column, I sit down with decision makers and I say, what do you want? And they mention some state of the world that they'd like to appear. And I say, that's not within your power, right? What I'm asking you is what you want everyone to do. That's an outcome that may or may not happen from people taking actions. But you're going into a negotiation, or you're trying to maneuver someone to accept your position. So what you need to work out is what you want them to do and what you're willing to do to get that. Yeah, that becomes your position. And for people to try and you can spend days with people who've been thinking about a decision for weeks and just trying to get them to understand what they actually want. It's just how complicated some of these kind of things are. Just asking them what they want and getting them to be clear and break it down and specify it can be a huge thing. And yet we're sending people off to analyze data using opaque models, and we think we're going to get answers. Clearly not, yeah. We don't even know what we want. It takes days to find out what we want. How is data going to find that out for us? It's not, clearly. And, for some really complex problems, there's a book called The End of Theory, which I'm drawing on here. And this is an example here of a model by a game theorist called Schelling. And it's about segregation. So he created a model where actually if you want 40% of the people in your neighborhood to be similar to you, let's say that I want 40% of my neighbors to be scientists so I can have discussion about them with them. Then it turns out that if you have that kind of preference for about maybe more than a third of the people that surround me are scientists or statisticians, say, then actually what that creates is massive segregation. Because you think, well, I'm happy to have a lot of non-statisticians around me, but that simple rule ends up with these massively segregated neighborhoods where all the statisticians are in little clusters and all the non-statisticians are in other clusters. And it's very difficult to see that just by looking at the simple individual rules. So we really need to have models that actually simulate this up to get the emergent behavior. But these are the kind of problems that we find that we care about. I mean, this is like the type of problem you would find in the financial meltdown in 2007. So economists are really good at steady state analysis, right? So when the economy is just ticking along and growing, economists can tell you quite a lot about it. Where their models fail is when the thing collapses. And I don't know about you guys, but the stuff I'm interested in is when the thing collapses. I'm not really that interested I'm kind of interested in steady state, but not that much. But when it hits the fan, that's when I care. And that's when the models kind of start to fail you. And to some degree, if we can build models, we don't have to worry about having these theories about kind of the shapes of curves and stuff like that. We can put some computing power together and have rules about how the individual agents act and create a virtual world and see how it operates and see what that tells us about the types of policy decisions we can make. So we create a world that runs faster and cheaper, and we tweak it and poke at it and see how the behavior operates. And we're not just taking the answers from that, we're using it to understand the dynamics of the system. Because in things like the financial crisis, the dynamics are what drives it. COVID, dynamics are what drives it, right? Are we seeing much kind of machine learning in COVID? Yeah, in the weeds of it, but they're not machine learning models on the news every day. right? It's good old standard mathematical modeling we're relying on there, statistical modeling. Machine learning's kind of like kind of disappeared a little bit, hiding away. It's like, yeah, okay, maybe, you know, we don't want to raise our heads too much here because this is the biggest thing, you know, for a century or more, yeah. And we haven't got much to say about it, really. It's that important. So again, you know, data, we're collecting data and data is useful there, but a lot of the time, you know, we're having to think beyond the data. And that brings us back to the kind of modeling that I'm talking about here in a lot of cases. Looking at systems models, models of how we understand epidemics actually evolve. These are kind of models of causality, causal models, basically. So that brings me to kind of like 45 minutes. Now I want to open up for questions. I'll hand back over to Darby and she can, you know, say a few things about Learning Tree and then hopefully fire some questions out. I hope she's been looking. I apologize, I haven't been looking at the questions. I've been kind of like in full flow, but hopefully I can pick up some of your questions now if you have any.
Thank you so much, Andrew. Yeah, we didn't get a whole lot of questions in the chat, but I did get some separate private ones, so I'll mention those. But anybody who has any questions, please feel free to post your questions in the chat box. I know several folks did raise their hand because we do have it muted for the webinar. We aren't able to unmute you for that, but if you do post your question in the chat box, we'll certainly get back to you. Awesome webinar, learned a lot of information. Thanks so much. And some folks did have some issues with their connection and such, Andrew. So I did make mention too that the recording, the on-demand webinar, as well as the slides will be available. So with that being said, I know it states it here, but regarding my Learning Tree, for those of you that have already participated in webinars or classes with Learning Tree, you'll be able to access this webinar on your My Learning Tree account. For anyone who is new to Learning Tree, you also have a My Learning Tree account just because you registered for this webinar. So in the next few days, you'll receive a follow-up email with details on how to activate your account and get access to this. And other webinars as well, great assets. So I don't know what's going on with the screen right now. I apologize. I think one of our technical folks will get that fixed up for you. So I apologize. You should have the chat feature back here in a moment where you can ask your question. So, but another thing I wanted to mention as far as those great assets, by attending this webinar, you actually get access to our data science collaboration space, where you have access to on-demand resources, including direct engagement from our data science SMEs. So that information will also be included in your email, but you can see kind of a screenshot there. Chris Mawada is one of our data science SMEs, as is Andrew, and they'll be part of this collaboration space. So that's perfect. And then finally, oh, there's our chat box. Okay. So we've also not reintroduced, but recently introduced our new Learning Tree Premium training bundles. So what I'm showing you here is our Decision Scientist certification bundle. This bundle includes the classes you see here. So the Introduction to Decision Analysis and the Introduction to Statistics, as well as the exams at the end of those. And then additional content as far as on-demand video, as well as ebook content. So yeah, that's part of the bundle that we have available. So if you're interested in that, go to our website, give us a call, you know, whatever works and you're able to do. Andrew, it looks like we've got a question from Claude. Can you elaborate on data lake?
Yep. So I'll answer the easy one first. My last name is Tait. I know that. So data lake. Yeah, so a data lake is really kind of the idea where you bring in data from all the different places that you might kind of like collect data. So let's say you've got transaction data, you bring it into a kind of big database, effectively some sort of repository. You bring in data about your customer service. So if people are kind of happy with your product or not happy with your product, you bring all that in. And basically you put it in one big data store where it's all available. And the benefit of that is that you can clean it all, you can actually fuse it all together, and you can make it available to everyone in your organization from a central place. The danger, so that's basically what a data lake is. I mean, if I need to go beyond that, I can talk a bit more detail, but that's the high level overview. There is a danger though with organizations that start doing data lakes. A lot of organizations, they start off, they'll employ they'll create a post of something like chief data officer or something like that. And then they set up a big project to create a data lake where we need to have all our data in one place, and we need to make sure it's all clean, and we need to make sure that we've got it all accessible, et cetera, et cetera. And this is fetishizing data again, right? I mean, it's obsessing about data, and they spend months, years actually putting these kind of lakes together without thinking about what they're going to do about them. So my advice to clients who are getting into data science is, that's a good end goal, but actually just start using kind of like making use of data and making use of decision-making technologies, obviously, and data within that framework to actually get going, because what you really want to do is make decisions locally. And so if you're using data locally because you need it in context, assuming that data is a big organization-wide project that then everyone just kind of draws from, is the wrong way to start it. And if you want to make your data the introduction of data science in your organization, if you want to make it really hard for yourself, start by building a data lake. Start from the data side and try and work towards the decisions. That's the hard way. Can work, but a lot of the time that fails and wastes a lot of money. What you really need to do is you need to start with decision makers and get those people on board, the stakeholders. Get people culturally thinking about how to be more scientific about decision making. Part of it is decision analysis, part of it is using data, and gradually move towards getting better and higher quality data while you're still adding value to the business, is what I always suggest. So data lakes are great, but don't start there, would be my advice if you're starting off. Does that make sense?
Makes sense to me, but not sure about Claude. We'll see. Dan Yang has asked if you could give an example of a good use of data science that solved a real-world problem.
Data science has solved a real-world problem. Just trying to think about kind of like things that can be talked about without kind of breaching privacy. I mean, I think that, my own use of data science. So, for example, all the time using data science. So, I mean, if I'm having to look at working out the odds, I do some work in the gambling area. So, looking at the odds of particular outcomes, I'm using data science all the time there. So, looking at data on historical events and actually using statistics, bringing those two things together and making that work. Looking at, done some work with looking at trying to fill in the gaps. So when you have public health policy things that you're trying to work out, and you do surveys in certain areas of the world where it's quite difficult to do a survey. So areas where there's can be war torn, or they're huge kind of like the geography is huge without much access to roads and much access to kind of like the internet and things like that. Then collecting data is actually quite a difficult thing. So we can use Bayesian analysis, for example, to actually be trying to fill in the gaps in our knowledge based on the limited survey data we have, and trying to work out, say that we're trying to work out the level of birth control in an area, or the level of kind of vaccination in an area, and we've got limited data. We can use data science and statistical models to actually try and fill in those gaps. And in my own work, I mean, I showed you models that I use. So say the confrontation analysis model, well, there, it's a case of using those particular models to work with senior, say, military decision makers, where I did a lot of the work, but I've used them in business as well, to actually look at modeling their current situation and what they want to get from their next discussion. So when you find senior generals are now diplomats, they're going around and kind of like, doing a lot of the negotiation. So they're the ones actually confronting the enemy. It's no longer kind of like, traditional warfare. We had kind of like soldiers running around with rifles at the front line shooting each other. a lot of modern military work is senior officers actually meeting their counterparts and trying to thrash things out. So actually, decision science and tools like confrontation analysis are helping us understand what we're trying to achieve and bringing to the fore the structure of the problem that you're facing and focusing on the bits that you need to actually focus on, because these problems seem intractable. But if we can model them, we can focus attention and say, you need to be asking these questions here, because if you're not asking those questions, you're not solving your problem. Any other questions you ask are not going to attack the part of the problem you need attacked. So it allows them to focus out of all the things they could possibly do. So yeah, I mean, decision science used in all sorts of places. I mean, Chevron is a company that runs on decision science. It's quite interesting. Every decision they make, you need to justify it with modeling and statistics, and so they're a great case study for this kind of thing.
I always find that kind of question interesting myself, Andrew. So just seeing how people actually use it. So I'm glad that they asked that. We had several more questions come in. I don't know that we're going to be able to get to them all, but Pamela Monroe is asking what you think about using Tableau, and then she followed that up with what analysis tools do you recommend?
I wish we could. I think I can see John Uni's name here. John Uni is another instructor. He's an expert in Tableau, and I kind of wish we could bring John in and get you the answer, get him to answer that question. But I guess we don't have the time. But yeah, I mean, I'm not a big Tableau user, but anything that kind of like is going to help you make sense of your data, I think is valuable. I mean, like I say, I'm a huge fan of data. I tend to not use point and click tools because I like to be able to document what I'm doing and be able to replicate it. So I tend to use Python and R when I'm actually doing my data science work. I find them to be more flexible than Tableau and Power BI, etc. And I do worry about this democratization of data thing I said, where people without the appropriate expertise actually might start using tools like Tableau, but that's not a fault of Tableau, that's a fault of the use of Tableau, obviously. So, as a tool, yeah, I mean, Tableau is very capable, Power BI, very capable. These are tools that Power BI, I've actually built dashboards for clients with before, so a lot of similarity with those tools. But I think that kind of like, the same issues arise. Whatever kind of data analysis tool you're using, the same kind of things apply. Is still focused on the data. And you still have to bring in statistical expertise. You still have to actually think about the decision you're trying to make before you go mining Tableau for some answers. So same sort of things that apply.
Perfect. And John did respond, Pamela. Well, he responded and he did mention that we just did that Power BI webinar a few weeks ago, and we also have a previous Tableau one. So Pamela, check out our website, the webinars page, and you can find those as well. Claude now asked, what data lake software do you recommend?
Oh, what data lake software I would recommend? I mean, I think that a lot of this data lake stuff is actually on the big platforms actually have solutions to these data lakes. So the places to go, I think, to start off with, when I'm working with companies, don't create your own stuff. Just use what AWS or Azure or Google Cloud actually have. I mean, the data lake is kind of like, often it's a combination of different technologies that you're actually using. I mean, when I'm trying to store a lot of data, I tend to use Elasticsearch. If I'm storing relatively unstructured data, I find that quite useful. A lot of Mongo if I'm storing kind of semi-structured data. So these are kind of tools that I tend to use when I'm actually storing data. But if you're looking to actually have a heterogeneous data lake, then I think the big platforms are the places to go. Really, the big cloud platforms, if you can put your stuff on the cloud.
Perfect. Thank you so much. And we are reaching the top of the hour, the end of our webinar now. So we did have a few more questions that were asked, but please feel free to give us a call. We can always get in touch with Andrew, one of our SMEs, for answers to your questions as well. So thank you so much for your time. Thank you, Andrew, for your time. I greatly appreciate you doing this webinar for us. So Again, please keep an eye out on your email. There will be some information about accessing this webinar on demand as well through your My Learning Tree account. So thank you so much, everyone. Have a great day.
Thank you, everyone, for attending.